Assalamualaikum and good morning. My name is Ahmad Zakir from Group 6, and our case study is case study 2, which is pipeline explosion at Putra. Now we will present about the background of the case study. Material gas distribution pipeline in Malaysia mainly use api 5L grade B, carbon steel and HDPE material. This pipeline support the rapid growth of urban infrastructure and residential area. Despite of high safety material, pipeline material can degrade over the time due to environmental, chemical and environmental factor. A major pipeline failure occurred in Putra Heights, a densely populated residential township in Selangor. The high pressure gas pipeline ruptured, causing an explosion and significant damage to surrounding property. The incident disrupted essential service and raised serious public safety concern. And move to our objective of the study is to identify the material involved in the pipeline failure, investigate the extent of material degradation, analyze the combined failure mechanism that caused the rupture, and propose three engineering solutions to improve pipeline reliability and future safety. Okay, thank you.
The Putra Heights incident involved a natural gas transmission pipeline operated by Petronas Gas Berhad. Since the exact material specification has not been publicly disclosed, this report focused on carbon steel line pipe, which is the standard material used in oil and gas pipeline systems. Steel is the most widely used material for hydrocarbon transportation, with pipelines primarily fabricated from carbon steel and low-alloy steel grade, specifically high-strength low-alloy API 5L X-grade steel ranging from X42 to X100 are the most widely reported, governed under ASTM A53, A106 and API 5L standards. As the primary pressure-containing element, carbon steel is designed to withstand internal gas pressure and external mechanical loads. However, in buried service, it is susceptible to external mechanical loading from ground movement, where prolonged soil settlement can induce fatigue and tensile overload at critical joints. Consistent with the confirmed cause of this incident from Bernama News.
Physical properties of material. The involved pipeline was a 36-inch high-pressure gas transmission line constructed from API 5L carbon steel by Petronas. It is not confirmed or reported from any source the specific material that was used for the pipeline, but it is assumed it was constructed from API 5L carbon steel because it is the widely used material for pipeline gas transmission line. And it is very important for us to understand the mechanical properties or the physical properties of the material in order to understand how the material behave under real operating condition such as pressure, heat, and long-term salt exposure. So there are several properties here, as we can see, is density, melting point, thermal conductivity, thermal expansion, electrical resistivity, and carbon content. We want to focus more on the carbon content because higher carbon content means higher perlite in the microstructure. This means the material will be a lot stronger and higher in strength, but reduce in toughness and higher in brittle. This will lead the material to be much more vulnerable to cracking.
So at the microscopic level, API 5L steel carbon has the combination of ferritic and pearlite microstructure, as we can see here from the diagram. The ferrite is the white area where the properties is soft and ductile. First, it also with a body-centered cubic crystal structure, which is the BCC structure, and then we have the pearlite darker area, which is the strong but brittle. Together, they give a pipeline a balance of strength and flexibility, but there are trade-off. Higher pearlite content increase the strength, but it also reduce the toughness, making it more vulnerable to cracking under repeated loading. Microscopic impurities called as the manganese sulfide, or in short as MNS, inclusion formed during the manufacturing, aligned like flat ribbons. They act as hydrogen traps. When the hydrogen atoms build up from the soil corrosion and diffuse into the metal and get trapped inside this MNS pocket, they will cause internal cracking until the surrounding grain boundaries crack. This phenomenon called as the hydrogen-induced cracking, or in short HIC. What makes this very dangerous is because it happens without any warning, since it happens inside the pipe wall with no visible warning on the surface. Diagram here shows the heat effective zones, also known as the HZ zones. So when pipeline segments are welded together, the extreme heat will permanently change the microstructure around surrounding the area of the welded zone. So there are several zones here, and the most important one need to be focused on is the CGHZ, also known as the coarse grain heat effective zone, located closest to the weld. In these zones, the grain grows very large due to the intense heat, which makes the region very hardest and high in strength, but also very brittle. This is where the cracks will likely to happen, especially under repeated mechanical loading. Based on serum report, they confirm that the fracture that happened during the incident occurred exactly at this welded joint. So how do all these material properties connect to the actual explosion? Since Serum already confirmed that the pipe met technical specification before the construction, it suggests that the metal itself wasn't defective. The real cause was long-term fatigue. The PSSC found that the soil settlement has caused the pipe to undergo a displacement, which causing the stress concentration right at the weakest point, which is the HZ of the welded joint. Over time, the fatigue cracks grew slowly until the pipe could no longer hold, and then resulting in tensile overload, rectal fracture, gas leakage, and finally ignition, causing the explosion. This is a classic example of how good material can still fail when the environment works against it long enough.
For chapter 4, mechanical properties and microstructures of material. Firstly, I would like to explain about mechanical properties. So, mechanical properties of a material can be described when the material is responding to an applied physical force, load, or stress to it. For this case, the pipeline material, which is API5L, grade B carbon steel, respond to forces from high pressure of gases and reacts to its mechanical properties from yield strength, tensile, ductility, and Young modulus. For the first property, the yield strength is its typical value is higher or equal to 241 megapascal, and it is used for maximum internal gas pressure the pipe can handle before deformation. The second property is tensile strength. It is usually higher or equal to 414 megapascal, maximum load bearing capacity before structural tearing. The third one is ductility or elongation. It is higher or equal to 23%. To understand the plastic deformation of the material, and it is used to confirm local hydrogen embrittlement by sharp drop in the property. And the last property is Young modulus. It is equal to 200 gigapascal, and it is used to measure the material's baseline elastic stiffness. So the second one is microstructural analysis. I will explain how the failure investigation of the Putra pipeline materials. So the first three pillars are the first three pillars of microstructural study is the base metal, the normal steel matrix consisting of ferrite perlite grain that provides the pipe's baseline mechanical properties. The second one is the well zone, HAZ, the heat affected zone, where intense thermal exposure permanently altered the grain size and phase stability. The third one is defect and path, microscopic traps like manganese sulfide, inclusion and the morphology of branching crack path. So the first one is base metal. I will explain in ferrite and pearlite microstructure. Ferrite microstructure is that it is naturally soft and flexible properties with high ductility, allowing elastic stretching, and it will prevent snapping under standard operating loads. The ferrite grains are usually light colored regions within the matrix. The second one is pearlite microstructure. It is usually dark areas and it provides the steel with its baseline structural strength, and it is filled with iron carbide or cementite as it cools, and it is act as the reinforcing component in the matrix. So combining both, the dual phase mixture of ferrite and pearlite offer a critical balance of strength and flexibility required for pipeline integrity. The next one is the well microstructure. The well microstructure is due to extreme thermal transformation. The intense heats during welding permanently altered the steel right next to the joint. So the grain growth occurred as the microstructure ferrite and pearlite grains swell from the extreme temperature. As the well cooled rapidly, the orderly structure was disrupted, creating a chaotic, tightly packed crystalline structure that differs entirely from base material. Basically, HAZ causes the base material and the joining to be different lah. And it is high brittleness. The rapid cooling transforms the ductile matrix into brittle, and it lacks the ability to deform elastically. And next is the internal stress. The rightly packed crystalline structure locks in massive internal stresses during the cooling phase. And lastly, crack initiation. Due to this factor, the HAZ is the primary site where cracks prefer to nucleate and begin their propagation. And last section is the traps and defects, or defects and paths. Firstly, manganese sulfide stringers. During the manufacturing, microscopic chemical impurities were flattened into long, dark microscopic ribbons called stringers. So it is occur as elongated dark lines under a microscope, and it cuts through healthy grain boundaries and act as traps for atomic hydrogen absorbed from soil corrosion. And this will continue to crack to crack propagation. This mechanism will be explained from stepwise cracking and branching. The first one, the gas will be trapped, as I explained, in manganese sulfide pocket expands, and it will build pressure until grain splits, creating a stepwise crack. Path is a crack crawl along weak grain boundaries. Then it will cause branching as path growth. Instead of clean break, a tree root network of tiny cracks forms, and it will cause lastly the failure total burst of the pipeline system.
Okay, now we are going to discuss on fabrication methods of API 5L carbon steel. So we start with the manufacturing process, which is the fabrication process begins with steel making and continuous castings, where the raw material, which is the steel, is processed into steel slabs, and then these slabs will be hot rolled into steel plates with the required dimensions and mechanical properties. Then these steel plates will be formed into cylindrical pipe, forming a pipeline gas, which is the manufacturing methods use UOE forming or spiral forming. And then the after the pipe shape is formed, the edge of the pipe will be joined by using the submerged arc welding or SAW. And then to ensure quality, after the pipe is joined, to ensure the quality and safety, the pipeline will undergo NDT, which is NDT. What does it mean by NDT? NDT is a non-destructive testing, which is testing that will be conducted after the pipeline is formed to detect any defects without damaging the material itself. So we have some testing which is they will be using ultrasonic testing and radiographic inspections to check whether there is any flaw in the pipes. And then finally, we will use protective coatings such as from this slide, you can see that they use 3-layer polyethylene, and which is applied to prevent from corrosion occur. And then hydrostatic testing is conducted to verify the integrity of the pipeline before it is put into the services. So next we will be discussing on the applications of API 5L carbon steel pipelines, which is there are some major applications on this pipeline, which is the most important application is in the transportation of natural gas within Malaysia's peninsular gas utilization, which is this transportation distribute natural gas from processing facilities to industrial users to power up these generation stations. And then other than natural gas transportation, API 5L carbon steel pipelines are also used in offshore, which is in oil and gas section to for the transmission of crude oil and petroleum product, because we know that API 5L carbon steel pipeline can withstand high internal pressure and over long distance. So these pipelines also commonly found in gas platforms, petrochemical plants, oil refineries, which is carbon steel demonstrates its excellent balance of strength, toughness, weldability, and reliability. And it cause the pipelines will be the most important material that be used in modern energy transportation system. So based on our analysis of the Putra Heights gas pipeline explosion, we propose three engineering recommendations to improve the pipeline safety to prevent from the similar incidents happens again. So our first recommendation is by using the advanced coating system, which is we use 3-layer polyethylene, which is decoatings. These coatings provide protections against corrosion or moisture penetration, which is it will help to extend the service life of pipelines. And our second recommendation is by strengthen the quality assurance during the fabrication and installation, which is it can be achieved through automated welding technologies and advanced non-destructive testing method, which is the NDT before, which is it will help to reduce the fabrication defects and improve the weld quality. And our last third recommendation, we like to add some integration of smart monitoring technologies, such as example we use include the fiber optic sensing system to detect any corrosion, leakage, and coating damage, and ground movement at an early stage before any failure happens.
For conclusion, the root cause is coating failure cause CP shielding and deep pitting corrosion in aggressive soil. Because of that, failure mechanism, cycling operating pressures propagated pitting into stress corrosion cracking, which is SCC. And the catastrophe happened. Progressive fault thinning led to structural overload rupture and ignition. The key information is the reactive maintenance is dangerously insufficient for aging underground infrastructure. So we need to replace it and upgrade to high toughness HSLA for crack resistance, which is we need to replace the pipe with more tough material, and we need always to active monitoring it by implement 3 LPE coatings alongside real-time fiber optic sensing.